So today's talk we shall go to the next part of semiconductor physics that we are discussing. So today we shall discuss about PN junction. Okay. So we shall discuss about the detailed physics of PN junction. So as I said that what is P and N. So P and N are the like two extrinsic semiconductors. Let's say this is P, this is N. So here we prepare the p-type extrinsic semiconductor by doping phosphorus ions in the silicon, whereas n-type we can make by boron doping in the silicon. Okay. Now, when we make a junction of such a p and n-type extrinsic semiconductor, so we cannot simply just put together like as I have plotted here, like just sandwich it. It's not a so simple process. Maybe in later step I can explain to you. So there are different ways. So either you can take a silicon piece and put you can diffuse the borons. Say if you want to make n-type, then at high temperature you can diffuse borons, or you can, there is another process called ion implantation, so that you can do either with boron or phosphorus, and then within a silicon sample you can make diffuse this boron and phosphorus separately, and you can make this PN junction. So there is a very detailed process how to make PN junction, that if we get time that we can discuss later, but important part now is that to understand the physics of a junction. If we make such a device where we put p-type extrinsic semiconductor and n-type extrinsic semiconductor, then what is going to happen at the junction? Okay, so so the band diagram of this p-type and n-type will be like, here is the p-type, so, and here is the n-type. So this is the conduction band, this is valence band, and where will lie the Fermi level? So if it is like, say, let's say the energy wise, this is EC, okay, and this is EV, okay, the energy of the valence band. The Fermi level for the p-type, it will lie very close to the valence band. So this is basically acceptor. So EA we are putting as EA, sorry, my mistake, this is the Fermi level. So this is the Fermi level, and here we are putting the Fermi level very close to the conduction band. Okay, so if we make a sandwich, will it become very simple, like just make a sandwich of P and N, and will its Fermi level, so this is EC and this is EV, and will there be Fermi level like this? Like this is again EF and here is EF? Answer is no, because now as you see, if you make a device, the Fermi level is a different position, which is not allowed for a device. So once you make a compound, or you make a, say, simple device where you have a PN junction like this, a material, it doesn't matter how many junctions you prepare, at the equilibrium condition the Fermi level is independent of the position. Fermi level EF has to be fixed with respect to the distance. Now let me explain you a little bit further. What do we mean by Fermi level will be fixed? So that let me come to that part first, because in the previous lecture also I told you that the Fermi level, like when I was discussing the diffusion, right, I told you that the Fermi level is independent in a equilibrium condition. Under equilibrium condition EF is independent of position, independent of x. Okay, so d of ef by dx, if you do, this should be equal to 0. That's why it doesn't matter where is your conduction band or a valence band, your Fermi level position will has to be continuous, so it has to place at a certain energy. Okay, now let me come to that part, how we can say such a, make such a comment like the Fermi level is independent of the position. So as I said to you, the under equilibrium condition in a device, the net current is 0. It doesn't matter what are the mechanism involved, whether it's a diffusion, drift, blah blah blah. At the equilibrium condition, when you don't apply external perturbation or a voltage, the net current in a sample has to have a 0. Okay, so let's consider, we are considering a p-type semiconductor, and your net current is jp, this is equal to 0. So that means the drift current and the diffusion current, whatever is there in the compound, in the sample, has to balance with each other. So the total drift plus total diffusion current density of the sample has to be 0. Now let's put back the expression of the drift and the diffusion process that I talk about. So in the, I think in the last class I have shown to you. So flux and diffusion. So as you see here, so this is the diffusion. So this is the diffusion current for a p-type extrinsic semiconductor, and the drift current is again is here. Okay, so now we put back these two in our equation here. So drift current is basically q into, okay, let me just change the color, it will be good. Okay, so q into mu p into p into e, this minus the diffusion current will be minus q into dp by dx equal to 0, where dp is basically the diffusion coefficient. Okay, now if we use, again we are going back to the last lecture, so we are going to use the Einstein relation. The diffusion current, the diffusion coefficient is kBT by q into mu p. So we put back this here. So if we put back use the Einstein relation, then this is equal to kBT divided by q into mu p. So we put back it here, then we get, so it will be q into mu p into p. Now we replace the electric field, the internal field, with the expression 1 by q into dei by dx. So ei is the energy level, and minus q into kBT divided by q into mu p into dp dx, this is equal to 0. So of course q goes, and now this we can write as mu p. So the total current is mu p into p d of ei by dx minus kBT into d of p divided by dx, this is actually equal to 0. Now let's calculate what is the expression of dp by dx. Okay, so if you recall, in my, I think the second lecture, I already explained to you what is the carrier concentration in the for the p type carrier, it will be equal to Ni into exponential of Ei minus Ef divided by kVt. So if we want to now calculate back dp dx, so what will be dp dx? So this is equal to Ni into exponential of again Ei minus Ef divided by kVt into derivative of d of dx into Ei minus Ef divided by kVt. So this term is again p. So this is equal to p into p divided by kVt into dEi by dx minus d of Ef divided by dx. So it comes from here, right? Now we put it back the same now we put back this same into here, okay, and let's see what is the expression it comes. So this is equal to Jp current equal to mu p into p dEi dx, and if we put back this one here, so kVt and kVt cut off, so basically minus p into dEi by dx plus p into dEf by dx. So this goes away. So this is equal to again mu p into p dEf by dx, and this term is equal to 0. So net result is, as you see, d of Ef by dx equal to 0. So in equilibrium condition for a device, the Fermi level has to be independent of that distance, okay. So Ef has to be constant throughout the device, okay. Fermi level, there is no change in Fermi level, okay. So this is going to be the key point when we want to plot the band diagram for a PN junction, because as you see, as I already explained earlier, for P and N, if we make PN junction P and N, so the Fermi level for P type is at the different position than N, but when you make a device of a PN junction, the Fermi level has to be fixed. It should not change with the distance, okay. So next key point is that before going there, I shall explain you something else also. What will happen when you make the junction? See, when you make a PN junction, your P type means this is put with holes, right? There are extra holes. Hole is the majority carrier, okay. Whereas N type means electron is the majority carrier, okay. So whenever you put a junction here and put P and N together, immediately the holes, it will start moving in this direction, and the extra electron, it will start moving in this direction, obviously, right? So so in P type, what we put phosphorus, sorry, in P type means we put P type means we put phosphorus ions, okay. So phosphorus means in, from the energy level point of view, this is EC and EV, and we have the acceptor levels right here. So we have the acceptor levels let's consider the concentration of acceptors is Na. Same time, for N type extrinsic semiconductor, we have extra donors, right? Because of which you have AC, EV, and we have here the donor level, right? So here you have ND, okay, the donor concentration. So donor concentrations, say boron ion, it has extra electron, right? It has extra electron. So once it gives away the electron, the carrier, the Nd ion, it becomes positive because now it has given the extra electron. So in the second lecture, I think, if you recall, I have told that this free carrier, the electron, which adds up to these majority carriers, once the electron goes away, this is a ionic charge particle which remains there. So this will be a positive, right? So let me put a different color. So there will be Nd plus. So once the electron is gone, then it will left with is a Nd plus charge. Same way, the acceptor levels, there is a deficiency of electron. So once it takes the electron, it becomes Na minus, right? Na minus charge carrier. So Na minus is in the p side and Nd plus is in the n side. So let me plot it once again. So you have the PN junction and this is the equilibrium position. This is p type, n type. So once you make the junction, there is going to be a the nearby region. What happens is very important. Okay, in this nearby region, once the holes goes into this direction and the electrons, it comes in this direction, at the barrier the holes and electrons will recombine. Okay, E minus and H recombine. So once electron and hole recombine, they vanishes, right? So both the charge carriers, it will vanish at the junction. Okay, so what it will leave is the ionic charge particles. So here it will leave with the acceptor minus because it takes the electron, and in this region it will leave left as Nd donor plus because it has left, it has given already donated the electrons. So in this region, this is called the depletion region. Okay, so depletion region means it depletes something. What it depletes is the carriers, because from the left hand side of the p type, it has already donated the holes, whereas from the n side it has already given the electrons, and once it recombines they vanishes. So this is the region where the charge carriers has disappeared. There is no charge carrier at all in this depletion region. That's why this is called depletion region. And what is left in this depletion region is this ionic charge particles, Na plus, Na minus and Nd plus. So as you see, once this charge particle remains, what it does is that you have a positive charge here. So again I should plot it. This is the equilibrium Pn, and you have here the negative charge particles, and here you have positive ionic radii, so ionic this particles. Okay, so what it will do is that this will generate a internal field. Okay, because of this positive and negative. So this internal field, what it will do is that, because see here you have the, this is p type, right? So this is p type, so it has a lot of extra holes, and n type means lot of extra electrons. So obviously these electrons and holes, they are free to move, right? But because of this internal field, this internal field will oppose the movement of holes and electrons in the opposite direction. Okay, so since inside there is electron n minus, so the force will be on the electron, because electron has negative charge, so the field will be in this direction, effective field on the electron. So the electrons which want to go in this direction, it will show the force, it will see the force applied from this depletion region, and these electrons cannot move further. Same way the holes, whichever want to go in this direction, because holes has positive q, positive charge, so this force, it will see this force, effective force, and the holes cannot move further. So under the equilibrium condition, what is going to happen is that you have this depletion region where there are local ionic charges. This is p type, this is n type. There are a lot of extra hole carriers, here lot of extra electron carriers. It is free to move, but the internal force will not allow the electrons to go here or the holes to go here. So this is the equilibrium condition for a p-n junction. Okay, now I'll show you the band diagram of the p-n junction, how it will look like. Okay, so we always plot, if you recall there in the second or third lecture, I have shown that if you plot the EK diagram, okay, so that is called band structure. Okay, but in this case we are plotting the band diagram. Okay, that is much easier to understand, that's why we stick to band diagram. Okay, so in the band diagram, as I already explained to you, under the equilibrium condition, there is no external force, nothing is there, and temperature is room temperature, it is room temperature, so no extra high heat energy we are putting, everything is in equilibrium. In that case, the Fermi level is independent of position, as I already derived, so Fermi level is independent. Now what it will be, now where will be the conduction band and the valence band? So as already explained to you, for the p type, this is the p type, right? And because in the deep of the p-n junction, it is at the end it is p type, so it will retain its behavior, and at the end extreme right, it is n type, right? So it has to retain its behavior. So this is EC, conduction band, and this is EV, valence band, and this is the Fermi level, EF. Okay, and EF minus EV, this ultimately gives you the p type concentration. Okay, p type carrier concentration in the p-n junction. And since in this region the carrier concentration, you are not changing the doping, right? So the difference here, the EF minus EV has to be fixed. Okay, now again when it comes to n type, okay, p-n junction, what it will do is that it will be this and this. This is EC and this is EV. Again here it is the, with respect to distance, it is not changing, it is fixed, there is no slope at all. Okay, so your EC minus, and this is EF, EC minus EF, this gives you the n type carrier concentration, right? Because this is at the end, here is the n type and here is the p type, it has to retain its behavior. And in between what it does is that It will simply go like this. You see, at the end, this is, we are talking about silicon compound. We dope with p type and make phosphorus doping and make p type, and we dope with the boron and make n type. So the band gap, which is the the band gap, which is this one, this is Eg, it has to be same everywhere. It does not matter. It has to be same everywhere. Whereas this is the junction which we are talking about. So this is the depletion region where there is no carriers. This is the depletion region of the p-n junction. Okay, where we have this slope. Throughout, wherever there is slope, that is the depletion region. And if you recall, in my previous class, in the carrier diffusion, I have shown to you, in the mobility, I think. Yeah, in this class, if you recall, I must have shown to you what is the effect on the field. What is the effect on the field? Where is it? Sorry. Okay, I can't find it. Yeah, this is here. So in presence of the field, you see here the bands, it tilts. So there is a slope change. Okay. So in the same way, in a p-n junction, you see there are the slope. Okay. So this slope comes because there is this internal field. And this internal field, it prevents the holes to move in this direction or the electrons to move in this direction. Okay, so this is the basic concept of p-n junction. Okay, so next I wanted to show you what is the direction of the field and how you can easily understand the field direction in this depletion region. Okay, so let me just plot this once again so that you understand. Okay, let's say this is the p type and we come here and we have this Fermi level which is fixed, and then again we come here. Sorry, I'm not good in the drawings. And this is the n region and this is p region, and this is the depletion. Sorry, this is the depletion region. Okay, now this is p and this is n type, this is Fermi level ef. Okay, and this is conduction and this is valence band. And now let's consider there is a electron in the same way that I already explained you in the diffusion process, the carrier diffusion. So if there is a electron, suppose sitting on the hilltop, so it will roll in the downwards, right? So same way as I explained in the diffusion, the field direction will be in this. Okay, in this direction. So this will be the internal field direction. Internal field. Okay. Now the electrons which are sitting here in this region, the excess electrons, the majority carriers in n-type extrinsic semiconductors, the electrons will try to move in this direction, and they have the charge of minus q, right? So the net force that this internal field will create on the charge is actually in this direction, because the electron charge is negative. Okay, so the effective force will be in this direction, which will oppose the electrons to move further into the depletion region. Same way for the holes holes has positive charge carriers, so plus q, then the force will act in this direction on the holes, so this will prevent further holes to move in positive x direction. Suppose this is x, so positive x direction into the depletion region. Okay, so this is the p-n junction. Now we want to talk about the potential which is there in this barrier, okay, in this junction. What is the potential that, let me draw it here, let me show you. So this is the total potential that will work on the charge carriers. So this is the net potential. Okay, we can tell this as the built-in potential. So this is called VBI, also called the built-in potential. Okay, built-in potential in the p-n junction. Let me plot it once again. So this is n type, and say this is this, then it comes here, and we have the Fermi level which is say lying here. Okay, so this is EF. Okay, and now the built-in potential which we are talking about is this much is the built-in potential VBI. Okay, now there is a simple relation which I already explained you in the previous class, that what is the relation of electric potential with the electric field. Okay, say for example, if V is the electric potential and if E is the potential energy, then what is the relation is that Q into V is equal to E. Okay, this is the relation. So the potential here, so the energy, potential energy here, because of the this built-in potential is basically Q into VBI. So this is the potential energy which is there at this because of this p-n junction. Okay, now what will be this energy? Because see that you can understand here is that, say we have taken one p-type extrinsic semiconductor and another n-type extrinsic semiconductor. Okay, so here it was the Fermi level earlier, right, for the p-type, whereas it was here, right, EF, the potential energy for the n-type. Now once you make the junction, it forms like this, right? So this Fermi level, it shifts, and because of this junction it forms like independent of the position, and it forms like this. So what is the net effect is that this, so as a result of this, you can think of like this is going up and this is going down, right? See, before making the junction, this was the position of the Fermi level and this was the position of the Fermi level. And once you make the junction, this is the effective Fermi level position. Whereas if you consider without doping, say let's say a intrinsic semiconductor where we don't have any doping, where the Fermi level supposed to be without considering whether it's a P or N, it doesn't matter. We have not considered any doping. So the Fermi level, it should be at the middle, like a intrinsic semiconductor, right? It has to be in the middle of the two band. So this is at the middle. So this is, let's say this is EI. Okay, EI is the intrinsic Fermi level. This is the intrinsic Fermi level. That means the Fermi level without considering the doping in the sample. Let's say we are, see both cases we are considering, let's say silicon. Okay, this side it is we are making p-type, means we are doping phosphorus and we are doping boron to make it nth type, right? So without doping the phosphorus or boron, this was the position of the Fermi level. Okay, and now Fermi level has shifted down because of your doping. So this is the net potential, okay, which has been generated because of the doping in the p type, whereas this is the potential which is generated in the n type. Okay, so let's say this is we call about Vn and this we call as Vp. Okay, so the potential, the the net potential which forms as a PN junction, so how much it will be? So VBI, the internal, the this built-in potential will be sum of this potential which is generated by the n type doping plus the Vp which is generated by the p type doping. Okay, so this is basically equal to Vn plus Vp. Okay, now let's see how much will be these voltages. Okay, again we draw the band diagram of the PN junction. Okay, so this is p type, this is n type, and here is the Fermi level. EF, this is the conduction in band energy, this is valence band energy. Okay, EV. Okay, again here is basically EV and here is basically EC. Okay, so let's say this is n type and this is n side, whereas this is p side, this is p side. Okay, now what will be the potential this is the internal, okay, this is EI, the intrinsic Fermi level. Okay, so now we want to consider what is the expression of the energy because of this one Vn. Okay, so Q into Vn. Okay, so this potential energy is basically the energy difference of this. Okay, because the carriers are here, we have introduced the donors level, right? Let's consider that nd is the donor consideration. So all the calculation for the PN junction, whatever we are doing, this is under the condition, there are two conditions we are considering. One, the temperature is room temperature 300 K, and two, all the dopant ions whatever we have considered here, whether it's a p type or n type, it doesn't matter, all dopant atoms are fully ionized. There is no bond. So for example, if we have put say 10 to the power 15 dopant ion in p type, we have 10 to the power 15 number of extra holes in the p type or in the same n type. In that condition, say for example in n type doping, consider if all the 10 to the power 15 the dopant atoms, it has released its electron, extra electrons, then we end up with Nd concentration of the ionized ions, right, in this n type, because it's fully ionized. Okay, same way, so this is the fully ionized. Same way in the p type we have Na, so this is the acceptor level concentration, right? So what will be the expression for this Vn? So Vn will be basically Ec minus Ef. So this potential energy difference in the this energy, potential energy. Now what will be the expression of Ec minus Ef? That if you recall my previous lecture, say I think I have explained it here. Fermi level. Yes, you see this expression. This expression. This is for the p type. Okay, p type extrinsic semiconductor. So what is the expression basically? Oh, sorry. PN junction. Okay. So for p type, it is p equal to Ni into exponential of Ei minus Ef divided by Kt. Okay. So this is the expression, and P is the extrinsic carrier concentration in p types, and now P is basically Na. So Na equal to Ni into exponential of Ei minus Ef divided by Kt. Whereas for n type semiconductor, what will be expression? N equal to Ni exponential of Ef minus Ei divided by Kt. So N is again, it is the donor concentration, ion concentration, because we are considering that all the it's fully ionized. Okay, so Nd equal to Ni exponential of Ef minus Ei divided by Kt. Okay, so what will be the relation of Ef minus Ei? Okay, so mod of Ef minus Ei. So right now we are not we are very particular about the your this signs. Okay, the sign of the charge carriers, because here we have considered Bn is the n type, so basically this is charge is minus q. So okay, let's put it, it's better, don't mix it, so use the absolute sign. So Ef minus Ei, so this is equal to Kt into log of Nd divided by Ni. Okay, Ni is the intrinsic carrier concentration. Okay, and Nd is the donor concentration. Okay, so if we plot back it here, so this is equal to minus of Kt into log of Nd by Ni. So what is the Vn value? So this gives you Vn, so this is equal to Kt by Q into log of Nd by Ni. So if you again use the similar relation for the p type, what will be the expression? Q into Vp. So this is equal to Ef minus Ev. So this is again, this is n type and this is in the p type region. So this is n type region and this is p type region. Okay, so this is the difference, which is the potential energy. Okay, so this, if you plug in the relation of with Na, you will get the relation with Kt divided by Q into Ln of Na divided by Ni. Okay, so what is the built-in potential which we are talking about? This built-in potential Vbi. So Vbi it will be, so Vbi is equal to Vn plus Vp. So this is equal to Kt divided by Q into log of Vn is basically Nd divided by Ni plus Kt divided by Q into Ln into Na divided by Ni. So this is log, addition means the within bracket it will be multiplication. So result is Kt divided by Q into Ln Nd into Na divided by Ni square. So this is the built-in potential energy in a PN junction, which is basically dependent on the multiplication of ND and Na. Where is Na? Na is the acceptor carrier concentration and ND is the donor carrier concentration. This is in the N type donor carrier concentration, whereas this is acceptor carrier concentration in the P type. Okay, and Ni is the intrinsic carrier concentration of the semiconductor we are talking about. Okay, so if it is a silicon compound, so Ni will come of the silicon's property, whereas depending on the external doping, that will determine what will happen, the value of Na and Nd, and depending on this relation we can calculate back what will be the built-in potential energy VBI. Okay, so the next part what we will talk about, this VBI, right? So we have discussed about VBI, what will be the potential energy here. Now what about this width that we are talking about, the depletion region width? So that let me discuss little bit, then we end today's class. So this is the PN junction and this is the Fermi level, this is EF. Okay, and here is we have the depletion region. So this is the depletion region, right? Depletion, this is the depletion region. Depletion region or also called the charge neutrality region. Okay, let's consider this is x equal to 0 coordinate. Okay, then this is, let's say this is Wn. Wn is the width of the depletion region inside the P, in the N side, in the N type doped region. Okay, whereas this is, if x equal to 0, let's consider minus Wp. So Wp is basically the width of the depletion region in the P type doped, in the P type doped region. Okay, now if there is charge neutrality, it is obviously that this region there is no free charge, right? Then the areal charge density in one region, this has to neutralize for the other, otherwise how you can get the equilibrium condition? So in order to achieve the equilibrium condition, under equilibrium, the areal charge density has to be same in both side of PN junction. Okay, so basically the areal charge density in this region has to be same in this region. So how to calculate the areal charge density? Okay, so as I explained to you, Na is the acceptor carrier concentration in P side, whereas Nd is the donor carrier concentration in the N side. Okay, and the width is basically Wp and here width is Wn. So if we multiply Na into Np, Na into Wp, so this is the areal charge density in the P type region. Okay, so this is density and this is the width, multiply is the carrier per unit area. Okay, this is the areal charge density. Okay, so now what the same it will be in the P type, so Nd into Wn. So the end result comes is Na into Wp equal to Nd into Wn. So if you want to achieve the charge neutrality condition in a p-type in a p-n junction. This is a very important relation which shows that the areal charge density has to be neutralized. So the multiplication of the carrier concentration, the acceptor carrier concentration in p-type with wp has to be same in both sides. So if you make a now if you make a p-n junction, okay, sorry, okay, let me plot like this. So if you make a p-n junction, this is p, this is n. Now this width in the, this is wp and this is wn. This, as you understand, this will heavily dependent on what is the concentration of na and nd. So basically, what is the carrier concentration you put in n type and what is the p type. Let's consider, for example, we make a heavily p type doped. So the p-type carrier concentration, let's say, is 10 to the power 18 centimeter minus cube, and a very low carrier concentration, very low doping in n-type, and let's say 10 to the power 15. There is a 3 order of magnitude difference. Then what will happen to these widths? If you put back this relation here, as you see, if Wn, for example, if it is 1000 nanometer, then what will be the value of Wp in order to maintain the charge neutrality? So this has to be 15 into 3 is 18. Already you have 18. So Wp has to be 1 nanometer. So if you have very low carrier concentration in the n side, the width will be much larger compared to the other side, because the p side is already heavily doped. P type is already 3 times larger than n type. So the width in the, so the depletion width, it will be much more inside the n type compared to the p type. Okay, so the p-n junction will shift accordingly. Now this idea, this concept I shall discuss much detail when we will come into the bias voltage in the p-n junction, etc. So those part maybe I can discuss in the next class. Okay, so today we'll stop it here. Sorry, students, while compiling the lecture, this lecture, I realized that I made a big mistake in the class from the beginning itself while considering the doping in p-n junction. So basically boron is we dope boron while preparing the phosphorus, sorry, the p type, and we dope phosphorus for the n type, which I already explained you, I think, in the second or the third lecture. So please rectify this, because here, as you see here, I have written in the wrong way. So I shall correct it in the, while I will put it the notes, I shall correct this wherever I have written boron and phosphorus I have mixed up. I will replace it properly and I shall again put it correctly in the notes. Okay, so just keep this in mind.